just told me to speak up. So, and if I'm speaking too quickly, told me to slow down. So, oh no, PowerPoint messed up the formatting. I did this in Keynote. So, anyway, this talk covers a bunch of the recent interesting things in the last couple of months that have been going on with malware and ransomware and things like that. And instead of going into like all the geopolitical stuff, I'm just going to show you a bunch of hex dumps. So, one of the things that was big in the news when I wrote these slides was the recent Flash 0-day, which is in the ActionScript 3 VM in Flash, and in fact, it's actually in the bytecode verifier. So the initial exploit was first seen in a number of targeted email attacks that were sent to a couple of institutions. Because Adobe Acrobat, if you embed a Flash file in it, it'll automatically run the Flash file when you open the document, and there's nowhere to turn it off. So if you're analyzing it, the way that a PDF is laid out is it's basically just a bunch of objects, like a big blob of text and like a font object and a bunch of images and a Flash object, say, and it's all in 7-bit ASCII for the most part, although strings can be 8-bit. And so the really quick way, if you want to analyze the PDF, is to go and install XPDF, and there's a tool that comes with it called PDF to source that lets you dump each of those little sections out of the PDF. And strangely, it doesn't actually do like all the sections at once. It just does them one at a time, so you can just do something like that. And then figure out which one's Flash file is good enough. And there's this open source project called Shockwave Flash Tools that has a program that'll dump the ActionScript out of the Flash file and disassemble it into all the essentially the VM assembly code. So there's a bunch of other metadata in the PDF. One of the things is like file creation dates and modification timestamps. And for this particular file, all the timestamps were in UTC+8, which is China or in Hong Kong. As if like the title, wasn't a giveaway. But I mean, if you're just looking at it and you don't have the right character set, you won't see the characters. But so anyway, there were two samples that were floating around that were slightly different. They were both based off apparently the same PDF to begin with, and just modified about 45 minutes apart for the two. And so there's a lot of metadata, which is the formatting's totally messed up on this slide, and I'm so tempted to go run up to the speaker room and grab my laptop and do it. But trust me, this was actually much more legible on my slides. I don't know if I should can I actually just go and grab my laptop and do it? I feel so embarrassed with having horribly mangled slides. Anyway, I'll keep going. So anyway, the actual embedded Flash file that had the exploit in it was called fancyball.fla, and I tracked down the original to it's in the SDK for Flash, and they basically just took it's a demonstration program for how to make a bouncing ball in ActionScript. So the attacker or the person who wrote the exploit basically just hollowed out the init function in it with a bunch of no-ops and then stuck this in, and this is the actual exploit here. The actual two instructions that trigger the fault are these two, and Adobe actually had a bug in their public bug database tracking system that if you do these two operations, you crash the ActionScript VM. But it had been around since December, and nobody really realized the significance of it until this exploit came out, and then Adobe quickly hid the bug from public view. So there was I have seen a slight variant of this exploit that was used in some browser-based attacks also, and I haven't finished analyzing this beyond that, figuring out that it's in the bytecode verifier, so that I'm not entirely certain if this multiplying these two values has any functional use or if it's just padding or something. So it's sort of on the to-do list. Good. So if you'll bear with me for a second. All right. Oh, wait, the adapter is up in the room. Okay, so I'll keep going. There's a couple other sections. Section 4 was a JPEG, or what seemed to be a JPEG, except the JPEG wasn't very well formed. If you actually try and view it, it was corrupt. There's a little bit of metadata in it. They probably just grabbed this off the web some ways. The gobbledygook in the JPEG, it actually turns out to be a full Windows PE executable file, and it's been ever so slightly encrypted with a single byte XOR key. And but this is a trend that has been I've been seeing a lot lately in a lot of Chinese malware is sort of hiding the presence of an executable file by stuffing a GIF or a JPEG on the front of it. So the other Shockwave flash file, and there was each of the two PDF samples had a different name. This is, if you're looking for the PDF itself, this is what it looks like for the reference. But they basically just do the heap spray in ActionScript, which is something new I hadn't actually seen before, and this site makes no sense at all because the formatting's all screwed up. So I'll fill time while they're searching for the VGA dongle. Did you find it? It's in the top of my backpack. So, is there any questions so far? Anyone? Oh. Doo-doo-doo. Doo-doo-doo-doo. Yeah, this is totally illegible. Anyway. The switching to PowerPoint thing was a very last second thing. So I apologize for this. That's not my backpack. And it might be faster if I just run up there and grab it myself. So that's it. Okay. Okay. All right. do. There, that's much better. So the funny thing, if you look at the heap spring, is sort of usually you fill memory with 12 and 13 byte and stuff like that. For some reason, they had this value, and I speculate that this is actually a typo in the original by the author of this exploit in the original ActionScript source code. Because if you accidentally type /0b/0b/0b instead of //0b/0b and so forth, you end up getting this value instead. So it didn't really have much of an effect on the exploit this time, because the instructions are also somewhat, as long as EBX points someplace in memory that's readable, this is effectively a no-op for the sled. So it turns out that the ActionScript bytecode is actually remarkably easy to read and somewhat similar to the input, so to speak. So you can see that all of the variables are stored in a little section by name in the original names. Things like strings and objects are like native types for the VM. So anyway, this particular code right here, you can see it basically assigns that string value to that variable and that string value to that. So in ActionScript, it would be written somewhat like that. Anyway, this is how loops are done. There's usually a loop. They usually stick a label opcode, which is it's sort of a special sort of no-op. It's to make the bytecode verifier's life easier when it's trying to figure out if all of the loops will actually point to regular places. Anyway, it basically means that this is the target of the jump in a loop, and so it's basically taking values A and B, adding them together, and getting the length, and checking to see if it's bigger than that, and if it's not, then it goes back up here and does it again. So it's a while loop. Same sort of deal. If you need to actually stick, raw, bytes into memory, you can use the write byte operator in the byte array. Does a bunch of that, and so on and so on. This is all very, very standard heap spray stuff. The shellcode itself is stuffed into memory with just a bunch of just writing it one byte at a time through like a couple hundred of these little byte operations. Comes out looking like this. All it does is it goes through memory, finds the slightly encrypted PDF from the other section of the PDF file, decrypts it, dumps out to the disk, and executes it. And the dropper then goes on and downloads all the other bits of the malware and so forth. So there's a lot of, as I was saying, one of the, traditionally, like most malware has not actually been stealthy in the slightest. It doesn't make any attempts to hide itself. It's all, straight plain text IRC or HTTP traffic, and anyone with a packet sniffer can see everything. And everyone's like, everyone asks me like, why don't the malware authors use like SSL? And they don't have to. Strangely, the way the environment is they can get away with using just straight plain text HTTP. But one of the trends that's starting to occur is people are starting to hide their communication up, so it's a little bit less blatantly obvious. One of the ways they've been doing that a lot is stuffing a GIF onto the beginning of executable files, because there's a number of products, I don't remember which companies have them, but they're sort of an IDS product that watches for Windows PE files, getting a copy of the network, and then raises some alert. And so if you just stick a GIF header or even just a full GIF onto the front of it, then the IDSs say, oh, that's just a GIF, and they ignore it. So Sometimes sometimes they're full, complete GIF files. Sometimes they're not. Typically, there was a downloader. Oops, sorry. There's a downloader that sort of formatted the files this way. There'd be a normal-looking GIF or JPEG on it, so you actually just load it up in an image viewer and look at it. But then it'd be, 300K long for like a 15 by 15 GIF, and so it's a pretty simple structure. It's the way that the downloader would know where to start extracting the exes from is you get the link for the offset for, sorry, mic's falling off. The length of the GIF is stored at the end of the file. So you read the D word off the end and jump to that offset, and then you get the length of the rest of the file. So you can like sort of add the numbers together and verify that you've got the whole thing. And then you have the length of the first exe, and that just carves that out. Then you have a D word for the length of the second exe, and it carves it out, and third one, and so forth. To sort of give a concrete example, this site's no longer up. So there's a full GIF here. It looks kind of like that. Anyway, it ends up out there. This was the end of the file, so it has the length of the GIF, which is, you can see, 403 hex. So 2 goes right there. Then this is the length of everything else in the file from there to there. I moved the end up here. Hopefully you're not confused by that. And you can add the numbers together and they'll kind of add up. So this exe is 3,200 bytes in hex long, or in base 16, and you can see it's an exe anyway. And second line, so forth. So, and the third one. I put too many examples in this. So, here's the second example. Basically, same thing. You get the length, go there. You get the length of the other stuff. There's an exe. That's how long it is. Anyway, this one actually, strangely, despite saying it's a GIF, isn't. Actually, it's a JPEG. Looks like that. Anyway, so there's a lot of botnet CNCs do everything in plain text, but they're kind of starting to hide it now because people with packet sniffers have been analyzing them. So they're starting to make it slightly more difficult than just looking at it in Wireshark. So so this one bot, it sends a request like this. It gets back something that looks like a JPEG, except it isn't actually. It's a little bit mangled. And then the next thing the host does after it gets this JPEG is it goes out and downloads an executable file from this address. And hang on a second. Sorry, the microphone's falling off. Downloads an executable from here, and there's sort of a cause and effect relationship between this. So whatever this information is must have come in from here. So it's not really a real JPEG if you try and look at it, obviously. And there are like two examples of it. You can see it's mostly the same bytes. I haven't actually hang on a second. I haven't actually totally decoded this one, so I don't have much more else to say with it, but to say about it. But there you go. Anyway, there's been a few examples of bots and malware and so forth actually doing crypto correctly. For most of the web-based stuff, the only one I've really seen doing it right is Lucky Sploit. And what they it's a toolkit, and and if you remember the talk that was immediately before this one on downloading your JavaScript in little chunks, it essentially has 3 chunks or 3 stages, and the first one has a complete RSA implementation written in JavaScript, and generates a random session key that it sends back to the lucky exploit server, which then encrypts the second stage of the JavaScript, which checks all the vulnerable versions of Flash and PDF and Java and whatnot are installed on the machine, so that in the third stage it knows which exploits to send. And with the RSA code and the BruCON code was written by by Tom Wu back in 2005. You can get the code off of Google Code. It uses math.random for filling the random numbered pool, which is somewhat significant if you're felt like cracking the crypto. And there's actually 2 RC4 functions in it, because in the Tom Wu code there was an RC4 function used just for filling the randomness pool, and then there's a separate RC4 function that the lucky exploit author put in that does the actual crypto of the JavaScript segments. So it's been slightly modified from the Tom Wu code. It may just be based on a later version because it has this function in it. So the first thing that lucky exploit does is it generates a 53-byte session key, which is always this value, and then it throws it away. And I don't know if why it does that. It's probably like leftover debugging code or something. And then it actually generates a real, random 53-byte value. It does it in it's not quite. It's 53 bytes with a base 64 symbol set, so it's not actually the full 8 bits for each of those. But I've seen a lot of JavaScript code that generates cookies using a similar algorithm. So 53-byte value stuffed into PKCS formatted blob, and with 8 bytes of randomness from the randomness pool and encrypted and sent back to the server. There's a public key in the JavaScript that is used for doing the encryption. And to sort of give an example, let's say that this is your random nonce. They just randomly happen to be AAAA. And you just randomly happen to have that as your 53-byte key. So when you pack it, it goes like this. It's ASN1, so that means that this is an integer, and that means this is a string, and so forth. You encrypt it with RSA, you get this here, and that's what's sent to the server in the URL, in the GET request. So the server sends back the second chunk of JavaScript, which is written like this. This is the encrypted blob of thing. This does the decryption here. So anyway, the value of next key is what was actually stuffed into the URL on the other side, and it's publicly known. And so it looks like, if you're just looking at this code by itself, you say, hey, wait a second, I know the value of next key that was spewed out on the wire. And it would be, you'd think it'd be like a horrible crypto mistake if they just revealed all their secret keys in doing this. But it turns out that RC4 decrypt in the lucky exploit thing actually takes the 53-byte nonce from the originally and adds it in, concatenates it in, so you end up getting a key like this for the RC4 value, and it doesn't have any more entropy than the original key did, since the public key that transforms that into that is known. But, well, no, actually, you don't know the nots. Sorry, never mind. And this is how it comes back. Checks for, flash version and so forth. So the other thing that's been using a lot of crypto lately is ransomware, which has sort of been a growing trend lately. It's been around for a really long time. There's actually I've seen like a couple of press reports going on about how this is brand new, and no, it's not. I've heard about this back in the 1980s. There was actually a Dick Tracy comic in the newspapers back in like 1989 that went through this whole scam, basically. So currently the only family of ransomware that's doing the crypto right is GP code, and actually the early versions didn't. They had their own home-rolled crypto that was trivial to crack. So in the current versions, they use the Windows Crypto API, and it basically does the crypto right. So my mic's flying off my head again. Excuse me. So basically, what the ransomware does is it searches your disk for all your documents, encrypts them all with a random RC4 key, takes a random RC4 key, encrypts it with RSA with the attackers or the extortionists' public key, and stores that on a file and says, if you want your files back, send this value back to this address. And the attacker then goes and encrypts it, gets the session key, stuffs it in the executable file, and sends the executable back to them. The bot will like delete it, clean up after itself. But this is pretty much, it's a pretty short program. This is pretty much all, the bulk of it is just calling these functions here. So you get it drops a message like this. For this particular variant, it would pop up an alert box for it. Yeah, I haven't changed anything. It really does say to recover your files. But this is another example. A lot of these seem to be Russian in origin. So there's a lot of bad crypto floating around because I know people, because this stuff isn't written by computer scientists, and I don't know, for your own reason, there's probably a lot. But if you're reversing, usually the quick way to find crypto, a lot of people, all they do is basically just repeatedly XOR some constant value. It's like the first crypto system everyone invents is like, they hear about one-time pad and they're like, oh my god, I'll create this great one-time pad system that uses the pad multiple times. And so everyone makes this mistake first. And so usually if you just disassemble the entire program, search for all the XOR operations, and then throw away, then grep out all of the XOR operations where the source and destination register are the same, you'll generally get like 5 XORs, and they'll generally at least one or two of them will be the crypto routine. So it's the quick way to do it. Otherwise, just tracing back and forth from the file read and file write operations and send and receive stuff will do it, because generally as soon as something is read, the next function called is the decryption routine. So so an example of bad crypto ransomware was the VS-Crypt Trojan. The author apparently called it Trojan encoder in Russian, but it was carried on a fake codec file. It pretended to be a Media Player 9 installer or something. Searches all your documents, encrypts them all, and says, send $10. Here, I'll show you the message. It sets the wallpaper on the desktop of the machine to this picture. And I wouldn't translate it, but basically the author of this wants 350 rubles, which is about $10, to send you the decryptor. So anyway, I analyzed it in about half an hour and saved everybody $10. So the so this is the crypto routine I used, and it turns out it's actually after I analyzed it, I did some web searches and I found the blog post of the guy who originally wrote the crypto routines, going about, here's this great crypto routine I just thought of. It does this, and basically you take the password, take the first byte of it and move it to the end. Then you take the second byte and you move it to the end, and then you take the third byte and move it to the end, and then you take the fourth byte and move it to the end. And this is an order-preserving operation. Then it uses the password that is shuffling, runs it through CRC32 and gets 4 bytes of output, and that's used as the key stream. And now, it sort of stands to reason that if you do this sort of shuffle with like a deck of cards or anything, you're eventually going to shuffle it back into the original order. And for the case of a password of about 38 characters, this happens after about 1,110 shuffles. So the key stream is only 4,440 bytes long. And making the password longer doesn't actually help. It's not a linear relationship. So a password of 50 characters actually has a shorter cycle, and it does start getting bigger, but it's some weird nonlinear thing. It bounces up and down. The only thing I was able to find about it was I don't know if everybody here is familiar with the online encyclopedia of integer sequences. It's like great. You type in a sequence of numbers, and I'll tell you the formula that produces it. Anyway, so for this particular one, it was basically that sequence times n minus 1. So, Fundu is a malware, family of malware that's been around for like a year or two, usually associated with fake AV software. It gets in your system and basically says, "Oh my God, you've got a virus on your system," and go to this website run by a bunch of Russian mobsters to download a fake AV program that'll keep protected. So earlier this year, it started dropping a program that would go and encrypt all your document files, and then it would pop up a little message box from the system tray saying that, oh my God, Windows has just detected file corruption, and click here to fix it. And it was like all, it all looked like an official Windows system dialog box. So anyway, I didn't actually have a copy at the time when I did this analysis. I didn't actually have a copy of the malware that was doing the encryption, but I did a copy of the decryptor, which is all I needed to know. So I got a couple of samples from some of the victims, and basically confirmed my suspicion that it was just doing a repeated XOR type thing. And the way that the File Fix Pro knows that a file has been encrypted or not is the bytes of the key have a mathematical relationship to each other, and so you can do this test on it using this key. For an example, you basically take the second byte. I'm going to call this one the first byte, and this one the third. This one the 0th byte, and this one the 4th byte, third byte, just to confuse everybody. Sorry, it makes sense if you're used to reading these in little endian format. So you basically take that value, divide it in half, or bit shift it down by 1. So it's 66, and if you take then if you XOR that value with that value, and it comes out to that value, then the key's good. Anyway, there's a very small key space. You can generate the entire key space with this small Perl program here. And anyway, so out of possibility of 32 bits, it only uses 2 to the 8th minus 1 of them. So statistically, about 1 time out of 16 million, you'll mistakenly find assuming a perfectly random distribution, which is not necessarily true for a lot of document files, you'll just randomly corrupt a file when you think it's decrypted and it isn't. So this is the original assembly code. If anyone actually wants me to go through this up on stage, like speak now, and anyone? Okay. But it basically, it's just doing the bit shift and XOR and so forth. So all the spam bots have been encrypting their templates lately. Symbot, for example, it generates this big string here off of like the system volume ID and the CPU ID and a bunch of the machine name and so forth. Anyway, it's basically just a big random number. Use that to apparently log in. I'm guessing L.php is for the login of this thing, and the botnet or the command and control server, just sets a regular cookie that it uses for all the further communication. It's just like just like any other PHP-based website. So I'm not entirely certain if D means get data, but generally it goes and goes and hang on a second. This string of stuff here actually has a meaning that's completely irrelevant. But when it does the request, it gets back a GIF file or something that looks like a GIF file, but it's not really. It's actually corrupted. The actual bits of GIF stop there, and then everything else is the actual spam template. So if you pull it, if you look at Symbot in IDA, you get this, and you eventually find there's this. This is how a lot of the crypto code ends up looking. Is you basically just have a loop, and then you've got like a simple operator in the middle for doing the decryption. So I'll zoom in on that. In this particular case, it uses subtract instead of XOR, and this is just in context. It checks to make sure that the input's more than like 15 bytes and stuff. So when you decrypt this, the result is this. So, ta-da! Anyway, and it's basically a spam template saying search through these bunch of files for anything that looks like an email address and send this particular message to these 5,000 email addresses or whatever. So that programming. So this is sort of one of the common myths here is that a lot of malware is very sophisticatedly written, and the people who are doing it know what they're doing, and that's not really true. Actually, most malware software is absolutely terrible code. It's absolutely full of bugs. It's a miracle it works at all. If you actually get a hold of some of the source code for some of them, it's rather obvious that whoever put them together doesn't know how to program. They just sort of cut and paste stuff from a bunch of other places. So this is an example of that, not an example of that. But when I was skimming through this code real fast, there's a FTP server in this particular bot, and I noticed this line right here, and I don't know, is there anybody who can like tell me what's wrong with this? The second argument is the FTP username that it gets off the wire. See? Yes, format spring. It pretty much will take anything you give this program as a as a username and just drop it into a printf, so that if you say if you say your username is %p, 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 it'll send you back the first 4 bytes off the stack. Anyway, I'm pretty sure it's a backdoor. Anyway, so here's an example of code that's written by someone who doesn't get it or doesn't know what they're doing. So it's called like this. Basically, they've got 4 bytes. They stuff them into a string, a dotted quad string, and then, or rather, they have an integer. They transform it into a dotted quad string, and I take the dotted quad string and immediately transform it back into the same integer again, which is completely pointless. The only reason we would do this is if they didn't realize that the IP address is an integer. This whole routine is just for people like to see the numbers, I guess, whoever wrote this. There's another function I saw skimming through this stuff. All it is checking to see if an IP address is in one of the RFC 1918 address spaces, 10 dot blah whatever, 192.168 dot whatever. Normally the way you do this is with a bit mask, but this person wrote this huge parsing routine to do it, and this is how you'd normally do it. So if I personally, if I was going to do it, I'd write it like this, but I'm just kind of showing off now. Anyway, so that's it. How am I for time? Good? Okay. So any questions? Anyone? Okay.
I'm a little bit confused because I see presentations here that says, well, almost like, watch out, the Chinese are coming, they know everything, and you end up with perception that there's quite very intelligent code out there, and on the other hand, you see a presentation like that shows that if we go really to the debugging level of what's out there, it's really very crappy, taken, copy-pasted from one to another.
Yep.
So where are we? Is it?
Actually, the place where you're starting to see the really good code is in the malware that's actually produces an income stream. So a lot of the fake AV stuff. Pretty much any malware that has a budget will generally have good code because they can afford to hire good programmers. So like with Srisby, for example, the Russian spammer who was operating the thing had enough money to go and actually pay some good programmer to like write a kernel rootkit for them and stuff like that. For Configure, whoever wrote Configure actually knew what they were doing, and it seemed much more like a research project and something to keep researchers busy than like what most malware is. But there's something like a lot of the script kiddie level type of malware, like a lot of RC bots and stuff like that. You'll just see glaring errors, not even in looking at the binary code, just looking at their IRC communication, where they'll like leave carriage return characters off, lines. They just have a line feed, but not a carriage return line feed for the mode command, but nothing else. There's things like that.
Okay, thank you, Julia.
Okay.